Okay, yeah, I would also like to thank the organizers. It's a really great location to speak. So we've already heard two talks by prominent theoretical physicists in the field of emergent gravity. So in this talk, I will not sort of put down a third account, but I will try to take a step back and see what all these accounts of emergent gravity have in common. And I will especially focus on why we actually believe that gravity and space-time are emergent phenomenon, and what are really the necessary ingredients that we need to really move forward and have a new paradigm for gravity. So this is based on work with Niels, and also, of course, with discussions with Eric. So to start with, I will just give a definition of emergent gravity from the literature. So yeah, gravitation is emergent if it's due to collective action of dynamics of more fundamental non-gravitational degrees of freedom. So I will refer to these non-gravitational degrees of freedoms as microstructure, as Padmanabhan also did, and Eric. But what's important in this framework is that you can actually, well, you can ask three separate questions. So what properties of gravity are emergent, say in general relativity? What kind of emergence is there at play? So what is really the principle behind this emergence? Is it something like statistical mechanics, for example? And thirdly, what is the microstructure from which gravity emerges? So to spell this out a bit more, so say in general relativity, what emerges is, for example, the metric, geodesic motion of particles, the Einstein field equations, and perhaps also the manifold. Yeah, so regarding the second question, we really want to answer the question, what is the universal principle behind emergence? And many authors think there's some kind of entropic reasoning behind this. So yeah, this is kind of what all the accounts have in common, one could say. So and thirdly, what is the microstructure? And some people refer to this as atoms of space-time. Now, when you really understand these three steps in one framework, you can also think about deviations of general relativity, as Eric already alluded to. So, for example, the area law for gravitational entropy always plays an important role in deriving general relativity, but then if you would change that area law, say, into a volume law, as Eric proposed in his paper from 2016, then you might derive deviations from general relativity. So yeah, here I just give an overview of some of the accounts in the literature. This is not complete at all, but I would like to make a distinction between, let's say, the thermodynamical or hydrodynamical accounts and what I call consistency conditions accounts. So in string theory, for example, you can also derive the Einstein equations from some kind of consistency condition on the beta functions. Okay. So what all these thermodynamic accounts have in common, and this is, has also already been mentioned, is that is the following observation, that typically you can derive thermodynamic equations from the Einstein equations. But then it's also possible to turn this logic around and to start with a thermodynamic first law and then derive the Einstein equations. So these equations, the Einstein equation and the thermodynamic equations on the left-hand side are really equivalent in a sense. But then, of course, the important question is, what is the origin of this entropy and this temperature? So what is really the microstructure from that counts? What are the degrees of freedoms that this entropy counts? And in string theory, of course, we have a precise understanding of this for black holes. So let me now get to why we believe that gravity is emergent. So you could distinguish between two approaches. So first, you could have a really bottom-up approach, like in string theory, where you know all the degrees of freedoms, your strings and d-branes, and then try to derive general relativity in a kind of low energy limit. Yeah, of course, sometimes that's very difficult to write down your full quantum theory of gravity. So another approach is to start top-down and sort of start from general relativity plus maybe quantum field theory effects, and then argue that gravity is emergent. So these arguments are really kind of plausibility or heuristic arguments, but nevertheless they might shed important light on the nature of gravity. And I will, in the rest of the talk, I will actually describe these three features of gravity and explain why they indicate that gravity is emergent. Okay, so an analogical reasoning takes the following form generically. So this is just maybe a bit formal, but so let's say that hydrodynamics or thermodynamics and general relativity are similar with respect to a bunch of features, and they are dissimilar with respect to other features. Now, since hydrodynamics has microstructure, like a fluid that consists of molecules, and GR is decisively similar to hydrodynamics, that implies that GR might also have microstructure. Okay, so these are the heuristic arguments that I will focus on, the first three. And arguably, if gravity would, well, the emergence of gravity actually explains these, in a sense, these three features. And without the emergence, these three features would be kind of mysteries, mystical features of gravity. Okay. So to start with black hole thermodynamics, well, this has been mentioned as well before, but I would just like to point out that there is like a precise map between the four laws of thermodynamics and the four laws of black hole mechanics, which was already done in 1973 by Bardeen, Carter, and Hawking. But at the time, of course, they didn't know that black holes radiate. So that's what Hawking derived 2 years later. And after Hawking's computation, people were really convinced that black holes are thermodynamic objects. So the argument that you could make here is that, well, thermodynamic systems have underlying microstructure, and the laws of black hole mechanics are really similar to the laws of thermodynamics. So black hole spacetimes should also have underlying microstructure. And this is, of course, what we see in string theory, where you can really construct a black hole out of d-branes. But you can do something more general or even stronger, and this is what Jacobson did in 95. So he really derived the field equations at every point in space-time from a thermodynamic first law. So his derivation really implies that, the following argument. So again, thermodynamic systems have underlying microstructure. Well, at each point in space-time, you can interpret the field equations as, well, what he calls an equation of state. So the field equations themselves are, so not black hole spacetimes or metrics, but the field equations themselves are due to underlying microstructure, and hence general relativity is fully emergent. Okay, so secondly, what you also find in the literature is that people refer to the universality of gravity, by which you mean the fact that gravity influences everything that carries energy and is also influenced by everything that carries energy. And technically, the universality of gravity is understood as the universal coupling of the metric to matter fields. And this universal property of gravity also reminds you of the universal characteristics of thermodynamic systems. So many systems can be described by thermodynamics. And in that sense, this universal property of gravity really is similar to universality of thermodynamics. Okay, yeah, so this is then a rough argument. So universality implies that there is coarse graining of degrees of freedoms, and hence there should be microstructure. But this argument is not completely sound because, not completely convincing, because universality of gravity can also just be understood as saying that gravity is a property of space-time, and space-time is really universal. Everything, all the particles move in space-time. So, I mean, this step is not a necessary step. And then also the last step, well, what kind of microstructure do you really expect? Because, well, if you have an RG flow in quantum field theory, then you wouldn't say that that is a case of emergence, in the sense of that you have non-trivial microstructure from which gravity emerges. So when I say microstructure, I really mean something like atoms of space-time. Okay, so thirdly, Eric also already talked about this. We have the holographic principle, which states that the maximal amount of entropy inside a given region does not exceed the area of its boundary, which was proposed by 't Hooft and later explored by Susskind. And this is really a new principle, or it's a principle of quantum gravity that even goes beyond GR. So I would like to make the distinction actually between the holographic principle and a holographic duality. So a duality, as in ADS-CFT, is a specific realization of this principle, and it goes actually much further in the sense that it states that all the degrees of freedom inside a specific space-time region can be described by a quantum theory living on the boundary of that space-time. And that's a much stronger statement than just the principle that the total entropy inside a given region is bounded by the area. Holography is often also linked to emergence, because physicists like to think about the bulk in being emergent from the boundary theory, for example, because the boundary theory is just is quantum mechanical and has no gravity. But this is really dependent on the fact that this duality is in some sense approximate and breaks down at a certain level, so that one side of the duality is more fundamental than the other. So let's say the boundary theory is more fundamental and the bulk emerges from the boundary. But in the case of ADS-CFT, it's not clear whether the duality is exact or approximate. But from the holographic principle itself, you could already argue that gravity has non-trivial microstructure, just very simply because in a local quantum field theory, you expect that the entropy scales with the volume, because there are degrees of freedoms at each point, at each location in space-time. I mean, this is a general expectation also in thermodynamics, that entropy scales with volume. However, the holographic principle implies that the entropy does not scale with volume, but with the area, which is the famous Bekenstein-Hawking entropy formula. So, I mean, combining these two results, you could say that the more fundamental theory underlying gravity is thus non-local. So it can't be a local quantum field theory. And this is, of course, also what we see in string theory, because strings are non-local, the branes are non-local objects, but also some people like to think about black hole entropy as due to quantum entanglement, which is also non-local. So this non-locality is a very important implication of the holographic principle. And well, you could say that non-local degrees of freedoms are necessary or inherently non-trivial. And hence gravity must emerge from some underlying non-trivial degrees of freedom. Okay, so to conclude, I described three analogical arguments, top-down arguments for the emergence of gravity. Horizon, thermodynamics, universality of gravity, and the holographic principle. And I think that, well, many authors view these three hints as really strong hints for the emergence of gravity. But more generally, the aim is to find a universal principle from which gravity emerges and that everybody agrees on in the string community and also in other communities. And the challenge is, of course, to identify this principle and also to identify the true microstructure underlying gravity. As developments in string theory show, that quantum information is really the key to this problem and to identifying the right microstructure. Thanks.
Thank you very much. Is there any question right now? Remark?